Okay, so this is the outline. And then let's get started. So, when you think about carbon sequestration in soils, soils have more carbon than the atmosphere or the above ground vegetation, okay? And mostly it's the soil organic carbon. So organic matter is 60% carbon, approximately. And the organic matter includes, a couple of different things, the living microbial biomass. There's an active fraction of the organic matter, the fresh materials added to the soil. And then there are the various decomposition products, the stuff that's a little more readily decomposable, and the other stuff that gets protected on mineral surfaces that lasts a little bit longer. And then there's black carbon. Black carbon is a byproduct of fossil fuel combustion, and it includes charred plant material, charcoal, and soot. There's a whole continuum of materials included under black carbon, and it's very common in urban areas. A couple of reasons why black carbon are important. At first, it's highly resistant to microbial degradation, much more resistant than regular plant-derived organic matter. It's got a higher carbon-oxygen ratio, and also has a higher affinity for contaminants, especially PAHs, trace metals somewhat, which is a good and bad thing in that it holds them very tightly, but the contaminants are usually there. Okay, here's a little more about black carbon. Like I said, a continuum from slightly charred material all the way to soot. Along that continuum, it decreases in recognizable plant structures, particle size, and reactivity or biodegradation. And an advantage of the black carbon is the residence time in soils is much longer than regular soil organic matter, okay? You're talking hundreds of thousands of years versus maybe 35, 50 years for regular soil organic matter, okay? Let's talk about soil inorganic carbon. That's usually not considered when we talk about carbon sequestration, but in some cases, it can actually sequester carbon. Calcium carbonate in soils can be divided into lithogenic or calcium carbonate in the parent material, which is usually limestone, and pedogenic or calcium carbonate that's formed in the soil. And the pedogenic can come from two sources, okay? You can get the dissolution of limestone. Okay, limestone dissolves, that calcium carbonate dissolves, and then it reprecipitates somewhere usually deeper in the soil profile. So is that actually tying up carbon dioxide from the atmosphere? Not really, because what you're doing is dissolving the calcium carbonate and then using that carbonate to reform calcium carbonate. So it's not really sequestering any net carbon dioxide from the atmosphere. But in some cases in soils, you have calcium silicate minerals. And when these calcium silicate minerals weather, they take carbon dioxide out of the atmosphere and form calcium carbonate. So if you do have calcium silicate minerals weathering instead of limestone, you actually do have net carbon sequestration in soils. Okay. So I'm going to show some data for some soils in New York City, and wanted to go over how we calculate the carbon stocks. What we usually do is we're trying to calculate a carbon density, okay, the amount of carbon to a selected depth. Usually it's a meter, and it's the amount of carbon per square meter. So it's the density per unit area. So to get this carbon density over a particular area, you sum up for each horizon to 1 meter, the soil organic carbon times the horizon thickness times the bulk density. Okay, so in doing your sampling, you have to sample for soil organic carbon for each horizon. You also have to get the bulk density. So you can calculate in this way the soil organic carbon stocks, and you can calculate the soil inorganic carbon stocks, okay, in the same way. One thing about the inorganic carbon stocks, one of the reasons we should consider them is that they have a much longer residence time in soil versus soil organic carbon. Okay, so organic carbon, you're talking maybe 35, 50 years, it turns over. So inorganic carbon, you're talking tens of thousands of years, 30 to 80,000 years, okay? So let's talk about the soil components in urban soils. You know, like most soils, there's mineral material derived from rocks. There's organic material derived from decaying plants and animals. One of the things that makes urban soils different is that you've got these human processed artifacts mixed into the soil in many areas. Okay, human processed artifacts include glass, brick, concrete, ash, etc. And they differ from natural soil materials in a couple of different ways. And some of these human processed artifacts are actually coarse fragments. They're greater than 2 millimeters, which we call discrete. Some of them are actually smaller than 2 millimeters and not as easy to recognize in the soil. And we call these particulate. So some of these artifacts can contain trace metals, pHs, other contaminants. Some can contain black carbon, things like ash, asphalt, unburnt coal. Some will raise soil pH and actually add calcium carbonate or inorganic carbon, okay? Concrete, which is predominantly calcium silicate and calcium oxide, can weather in soils, raise the pH, and add calcium carbonate when that calcium precipitates. Some artifacts can weather to amorphous clays, sulfides, other non-native minerals that you wouldn't expect in that particular soil. And it's to the point now where most classification systems for soils will differentiate soils with a significant amount of artifacts, okay? And it's usually estimated by volume, and 10% volume is a common cutoff for artifacts in soils. So let's talk a little bit about calcium carbonate in urban soils. Concrete weathering, it's very similar to that calcium silicate weathering. You get the formation of calcium carbonate. Here's a little factoid, a paper in England. They crushed concrete, put it on top of the soil, and in just 18 months, they estimated that they were removing 85 tons of carbon dioxide per hectare by the precipitation of calcium carbonate. However, when they manufacture cement, it uses quite a bit of calcium carbonate. And it's estimated that that's responsible for about 5% of global carbon dioxide emissions. So when you form calcium carbonate from concrete and take all that carbon dioxide out of the atmosphere, it's probably not net carbon sequestration. You're probably just making up for some of the CO2 that was emitted when you made the concrete in the first place. Okay. And here's a picture of some of our secondary calcium carbonates in New York City soils. What you see is that calcium carbonate is actually acting as a cementing agent and holding together sand and coarse fragment grains. If you were to get an eyedropper and put some 10% HCl on those, they would probably fizz like crazy. So calcium carbonate, patagenically formed calcium carbonate, is pretty common in a lot of urban soils, especially ones around the sidewalks and concrete areas. Okay, so let's talk about urban soils in general. There's similarities in urban soils globally, but the urban soil pattern is unique for every city and sort of depends on the geography and geology. the land use history and types of disturbance and the management practices. Okay. So here's the New York City. It's got a good variety of geology and geomorphology. There's 3 different physiographic provinces. Each have their own type of rocks, each with their own landscapes. The whole city was glaciated. The ice sheet probably left around 20,000 years or so ago. So there's areas of shallow and deep till. There's a terminal moraine, which I marked in yellow, running right through the middle of the city. There's glacial till to the north of that terminal moraine and glacial meltwater deposits to the south of that moraine. There's deposits after the ice sheet moved away, alluvial deposits along the rivers. There was quite a bit of tidal marsh, there's a little bit left. And there's a lot of anthropogenic disturbance. Let's talk a little bit about the development, historical development. There's 5 boroughs or counties, and 4 of the 5 are islands. It's not too terribly big, and there was always limited room for expansion. Okay. And because there was limited room for expansion, the Europeans tried to create a little more room by filling the wetlands, which the Dutch were pretty good at, and expanding the shoreline, which the English were pretty good at. And to do this, to create more land, because there was limited room for expansion, they used waste materials, okay? Demolition debris, dredge spoils, coal ash, and that's really has had an effect on the soils in New York City. Okay? So in our soil survey, we differentiated 3 types of, let's say, soils or map units. There were some native soils left in New York City, okay? Things that were deposited naturally. There's some glacial till soils, some glacial outwash soils. There are some marine sands, particular sand dunes, and some tidal marsh. But there are an awful lot of soils in either human altered or human transported materials, okay? Human altered would be a soil that was physically disturbed, maybe the horizonation altered, maybe thrown back in the hole. Humans transported when fill material was brought in from outside that area and a new parent material created. And these soils in either human altered or human transported materials include soils with clean fill, that is soils with not many human artifacts in it, soils in dredge spoils, okay? A lot of areas were dredged and the stuff put on land, okay? Fill from construction debris. There's some areas of municipal solid waste landfill, and there are a few areas of soils actually formed in coal ash. Okay? And then we differentiated also those miscellaneous areas or soils where we couldn't really map a particular soil. And the most important of those is what we called urban land, or the sealed soils, the soils that are underneath the pavement or buildings. Okay? So we've got native soils, soils in human altered, human transported materials, and miscellaneous areas or non-soils. And you could sort of look at these soils in a continuum of disturbance, okay? Native soils on the left, the human altered soil where you destroy all the horizonation, backfill it again. Human transported when you start dragging artifacts into the soil, increasing amount of artifacts. And then probably the maximally disturbed is when you seal the soil over, okay, cut it off from air and water exchange. So based on the survey here, the citywide totals, okay, 63% of the area is actually pavement and buildings in the city, about 28% human altered and human transported soils, about 9% native soils, and 1% those other areas, beaches, bedrock outcrops. And these totals vary by borough. Manhattan, the heart of the city, has the most sealed soils or pavement and buildings. And Staten Island has got probably the most native soils left. Okay. And if we were to look at the different types of soils within those groups, here's a little bit of the pedodiversity. Okay, the sealed soils, 63%. The next highest soil type is actually the clean fill, and the artifactual fill, the stuff from construction debris, dredge fill. And among the native soils, there's some brown glacial till soils, some red glacial till soils, tidal marsh soils, each making up about 2% of the land area. Okay, and each of these types, parent material types, would include one or at least one or more different soil series. Okay. So here are the organic carbon stocks in these soils. Okay. And I have them listed in order of the amount of carbon kilograms of soil organic carbon per square meter. And of all the soil types, the coal ash soils have the most soil organic carbon. It's because they're almost a very high percentage of black carbon in these soils. They don't take up much of the land area, however, only 0.1%. Next highest are the tidal marsh, okay, 46.33 kilograms soil organic carbon per meter square. They make up 2% of the land area. Okay. The artifactual fill, construction debris fill has got a lot of black carbon in it as well, and that's got a pretty high value. And then the glacial outwash soils, okay. The clean fill is next, and then the glacial till soils. One point I wanted to make was that the soils in the glacial outwash, the glacial till, are all in woodland vegetation, which we commonly think of as having high amounts of carbon in it. Whereas these clean fill soils are under turf. And one of the surprises looking at the carbon stocks was that you can get just about as much carbon tied up under turf as you can in the woodlands. And I did look at soil inorganic carbon stocks, and the construction debris fill, which has got a lot of concrete in it, actually does contribute a little soil inorganic carbon, 2.8. The sealed soils, those under the pavement, well, they're actually loaded with calcium carbonate. We know that just by adding 10% HCl to the soil material and looking at the reaction. But we did not collect any lab samples for calcium carbonate analysis. And I really regret this, because I think the sealed soils will have even more soil inorganic carbon than some of those artifactual fill soils. And they make up a whole lot more area. So it's probably a significant amount of soil inorganic carbon under the pavement and buildings. To put these numbers in perspective, I dug up some data on some Arizona soils. Calcium carbonate is more important in the profile in soils in the arid landscapes. And there's some values for iridosols in Arizona, entosols, mollisols, and alpha sols. And the iridosols have the highest amount, 33.9. What was interesting is that the soil inorganic carbon in these iridosols is 10 times the soil organic carbon in these soils. And I wanted to show you how the carbon is distributed in a couple of sample soils. First, here's one of the native soils. This one is in glacial outwash, and it's in the woodlands. And there's the horizons We did quite a bit of splitting, you could see in this soil profile. There's the thickness. There's the soil organic carbon down through the profile, and there's the bulk density. So you would get the carbon stocks by multiplying thickness, soil organic carbon, bulk density, and summing it up. And what I wanted to show out here was in the native soils, the soil organic carbon is really concentrated near the surface. Okay, it's all near the surface, and they're all pretty thin layers there. Okay, and that's unlike some of your anthropogenic soils. Here's an artifactual fill soil, one of those soils in construction debris. Okay, you can see first the horizons are thicker, and look at that organic carbon concentration, and it just sort of varies, but it's pretty high throughout the whole profile. Okay, a lot of black carbon in there, ash, asphalt, and this one's also got some soil inorganic carbon. Okay, carbon stocks in this profile, 61 kilograms of soil organic carbon and 3.21 kilograms of inorganic carbon. And here's one of those soils under clean fill under turf. And horizons are, maybe in between the thickness of the wooded soil and the artifactual fill soil. Carbon contents are sort of in between, but they're a little more consistent down through the profile. Okay. And like I said, soils under turf grass can store as much carbon as those in woodlands in urban areas, which was surprising. And then there's a sealed soil. Sealed soils don't have as much carbon as any of the other soils. One of the big reasons is that the topsoil is usually stripped off, or no topsoil is usually buried under these soils. So low organic carbon, sometimes a higher bulk density in these soils because they're compacted. And we did not calculate any soil inorganic carbon, but I would bet that there's a considerable amount in these soils. Okay, so here's the totals. So the average for the city was 10.41 kilograms per square meter. If you were to calculate an average, excluding all those sealed areas, including the pavement and buildings, it would be 17.96. And those are pretty good values. Here are some values from a study we did in New Jersey looking at carbon stocks on forest land and carbon stocks on cropland. So if you were to look at the citywide average, it's higher than the values for cropland in New Jersey. And if you were to look at the average in unsealed areas in the city, that's actually higher than the forest land in New Jersey. So that's a considerable amount of carbon. And here was an estimate from a 2006 paper on urban soils. So I think a lot of the current research is showing that there's a lot more carbon in urban soils than original estimates. Okay. And here's the total citywide in megagrams. And I wanted to show you what each soil contributes to the percentage citywide. So the sealed soils, even though there's not a whole lot of carbon in them, they do make up the bulk of the area, so they constitute more than a third of the soil carbon stocks citywide. The clean fill soils are up there, and the artifactual or construction debris fill soils are up there. Tidal marsh, about 9% of the citywide carbon stocks. Okay, maintaining and enhancing urban carbon stocks. The way to do it, increase both soil organic carbon and inorganic carbon inputs, and try and increase the residence time. And this was from a pretty good paper by Klaus Lorenz and Ratan Lau from Ohio State University. I'll give you a list of papers in a minute. But first of all, add soil organic matter, common sense, grass clippings, yard waste, compost, mulch. Optimize net primary productivity in your soils, and make your plant selection for increased vegetative growth, maybe production of root-derived soil organic carbon, something like grasses. To make carbon more resistant to decomposition, bury it deep in the profile. Mix it with mineral material, because when organic matter is mixed with mineral material, that mineral material exerts a protective effect, protects it from decomposition. Adding calcium also protects it from decomposition. Bury more carbon material to soils before sealing them. Okay. Most of the research shows that microbial activity is less in soils underneath the pavement and buildings. So adding carbon to those soils, any added carbon to those soils will be more resistant to decomposition. And creating biochar, since black carbon has a much longer residence time, and New York City has a lot of compost. Maybe we could look into creating biochar from New York City compost. Planting more trees. The soil under the trees has more time for soil organic carbon accumulation. And adding calcium-bearing waste to promote calcium carbonate formation, so inorganic carbon formation. But I would bet that there's a considerable amount in these soils. Okay, so here's the totals. So the average for the city was 10.41 kilograms per square meter. If you were to calculate an average, excluding all those sealed areas, excluding the pavement and buildings, it would be 17.96. And those are pretty good values. Here are some values from a study we did in New Jersey looking at carbon stocks on forest land and carbon stocks on cropland. So if you were to look at the citywide average, it's higher than the values for cropland in New Jersey. And if you were to look at the average in unsealed areas in the city, that's actually higher than the forest land in New Jersey. So that's a considerable amount of carbon. And here was an estimate from a 2006 paper on urban soils. So I think a lot of the current research is showing that there's a lot more carbon in urban soils than original estimates. Okay. And here's the total citywide in megagrams. And I wanted to show you what each soil contributes to the percentage citywide. So the sealed soils, even though there's not a whole lot of carbon in them, they do make up the bulk of the area, so they constitute more than a third of the soil carbon stocks citywide. The clean fill soils are up there, and the artifactual or construction debris fill soils are up there. Tidal marsh, about 9% of the citywide carbon stocks. Okay, maintaining and enhancing urban carbon stocks. The way to do it: increase both soil organic carbon and inorganic carbon inputs, and try and increase the residence time. And this was from a pretty good paper by Klaus Lorenz and Ratan Lau from Ohio State University. I'll give you a list of papers in a minute. But first of all, add soil organic matter, common sense, grass clippings, yard waste, compost, mulch. Optimize net primary productivity in your soils, and make your plant selection for increased vegetative growth, maybe production of root-derived soil organic carbon, something like grasses. To make carbon more resistant to decomposition, bury it deep in the profile. Mix it with mineral material, because when organic matter is mixed with mineral material, that mineral material exerts a protective effect, protects it from decomposition. Adding calcium also protects it from decomposition. Bury more carbon material to soils before sealing them. Okay. Most of the research shows that microbial activity is less in soils that are in soils underneath the pavement and buildings. So adding carbon to those soils, any added carbon to those soils will be more resistant to decomposition. And creating biochar, since black carbon has a much longer residence time, and New York City has a lot of compost. Maybe we could look into creating biochar from New York City compost. Planting more trees. The soil under the trees has more time for soil organic carbon accumulation. And adding calcium-bearing waste to promote calcium carbonate formation, so inorganic carbon formation. Okay, so these are some of the papers, and I could send these papers to your professor, and if anybody's interested in reading any of those. But the first two are on black carbon. The next three are on soil inorganic carbon. The one in orange is on the soil organic carbon stocks comparing New York City and Paris. And there's two on carbon sequestration potential in terrestrial ecosystems. Okay, so to summarize, soils in urban areas likely store more carbon than initially estimated. Okay. The tidal marsh and woodland soils make up about 17% of terrestrial soil organic carbon stocks in New York City. Surprising that soils under turf can store as much soil organic carbon as the woodland ones. The construction debris laden soils and coal ash soils make about 20% of the soil organic carbon stocks. It's mostly black carbon. There is some soil inorganic carbon sequestration in New York City. There's likely much more, but we need to get some data on that. And enhancing efforts include increasing the inputs and trying to increase the residence time.